Hello everyone. Hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today, we will go through the core concepts entitled as the application of GIS in reservoir sedimentation analysis. The most critical challenge in the water resource management is the reservoir sedimentation. Every dam built eventually loses its storage capacity, or that dam eventually lose its storage capacity due to that accumulation of silt content and the sediment accumulation. Traditionally, or basically, measuring this is not a simple task. This is the most tedious process or slow process, expensive process involving manual hydrographic surveys. Nowadays, we can use GIS and remote sensing tool for more efficient, non-intrusive way to estimate sedimentation, rate of sedimentation, and the prediction of the amount of sediments remaining useful life of reservoir. So GIS is used to monitor sediments deposition in reservoir, to estimate the storage, or to estimate the storage loss, and the plan maintenance is the major objective behind that GIS application. Satellite data is more feasible for the comparison over time, which is the working principle for that reservoir sedimentation. So the time series analysis and the high accuracy are the characteristics of that GIS application, where we can maintain the dam safety and the lifespan assessment. So which is more helpful in degrading and reservoir management. So reservoir sedimentation is the gradual filling of reservoir with soil particles or nothing but a silt carried by inflowing rivers. This process reduces that live storage needed for irrigation and power generation. The dead storage is also minimized by the accumulation of sediment at the bottom of any reservoir or any catchment. For any civil engineer, the excessive sedimentation is a major threat to infrastructural sustainability. By using that GIS tool, we can model the entire catchment area to identify the erosion hotspots, means the areas contributing most silt or the area accumulating large amount of sediments, allowing us to plan mitigation strategies like check dams construction or the afforestation more effectively. We have to increase the tree plantation to minimize the erosion or the materials who are flowing with respect to the runoff to the nearby catchment. The role of remote sensing, or the major activity by the remote sensing in sedimentation, is the monitoring. Satellite sensors can detect the water spread area of reservoir at different water levels throughout the year. Because sediment accumulation changes the depth area capacity relationship of the reservoir, these changes become visible in satellite imagery over the time. By comparing historical images with respect to the current data, we can see that where the reservoir is becoming shallower, or where the large amount of sedimentation accumulated. This remote sensing monitoring is significantly cheaper than physical dredging or underwater sonar surveys for large scale reservoirs. So sedimentation is nothing but a natural process of soil erosion settling in the quiet waters of the impoundment or any type of the basement of any dam. It progressively converts useful water storage into the dead capacity. We have to maintain the live storage or usable water capacity as much as, so that the stored water will be effectively used in the nearby command area. Now, causes of sedimentation, which is the part where sedimentation occurs due to the factors such as steep slopes, high rainfall intensity, soil erodibility, and deforestation, which increase soil erosion and the sediment transport into reservoir by using the way of means of rivers or any streams. The slide highlights that, or the digital elevation model highlights that the hydrological factors like runoff velocity, geological factors like soil type and erodibility, and anthropogenic factors such as land use changes and vegetation removal affecting sedimentation processes. The 4M are used in the engineering are measurement, mapping, monitoring, modeling. So these 4M are the basic explanation of the causes of sedimentation, or we can measure that sediments, we can map the accumulation of sediment, we can monitor the flowing runoff with respect to the sediment, and we can create a model to monitor this all sediment flow from various zone or any watershed area. So what are the factors behind that cause of sedimentation? Hydrological factors, geological factors, and anthropogenic factors. So by using that remote sensing and GIS tool, we can measure, we can map, we can monitor, and we can prepare the model to gather or to capture the sedimentation by analyzing terrain, land cover, rainfall, and watershed characteristics for suitable, sustainable reservoir and watershed management. Moving towards the estimation point of view, estimation of sedimentation, which is the most important concept, where where transitioning from manual discrete sampling to continuous remote monitoring. Historically, engineers calculated sediment by measuring the load at the water body's inlet versus its outlet. I repeat, historically, engineers calculate the sediment by measuring the load, or we can say that weight, or we can say that the accumulation of sediments at the water body's inlet versus its outlet. This is paired with hydrographic survey, where boats use sonar to map the underwater terrain, which is also called as a bathymetry, and detect physical buildup on the bed, or detect the physical accumulation of silt on the bed. The right side of the slide shows a shift toward using satellites to monitor water bodies from space. Altimetry specifically measures the height of the water surface, or that sonar system or signals measures the height of the water surface and the surrounding land, allowing engineers to detect topographical changes and sediment accumulation over vast area, sometimes inaccessible areas too. By integrating these remote sensing data points into a geographic information system, civil engineers move from discrete sampling, or we can say that occasional checks, to the continuous monitoring. This provides a real-time digital record of how sediment moves and settles, which is vital for the long-term maintenance of any type of dams or any type of reservoirs. So, inflow-outflow method is used for the measurement of sediment load at the inlet level versus outlet level. Here, the contour method for calculation or counting the volume. The contour line connects points of equal elevation, representing the intersection of the Earth's surface with a horizontal plane. Means the Earth's surface with a series of horizontal planes, allowing engineers to visualize 3D terrain on a 2D digital surface or 2D digital interface. Area integration for volume and the transition from manual surveying to the remote sensing are the tools for that contour method, where we can measure the actual volume. This method involves calculating the gross sectional area enclosed by each successive contour. This method involves calculating the gross sectional area enclosed by each successive contour. In civil engineering domain, the GIS software automatically integrates these tag areas over a specific elevation height to determine the total volume of a reservoir or a sediment buildup. So transitioning from manual surveying to the remote sensing allows for the high precision creation of digital elevation models. These digital models facilitate the successive horizontal contour plane, which shows on the slide, enabling monitoring of reservoir, continuous monitoring of reservoir or dam capacity without physical drainage. Digital elevation model is also a base or a crucial for the volume sedimentation estimation. So the basic concept is that it's in any raster image, the geographical information system which provides the information for that image with respect to the elevation, the surface is modeled as a continuous grid of cells. So in raster-based GIS, the terrain is represented as a continuous grid of individual squares called cells. This structure is often derived from a team, which is a triangulated irregular network interpolation, which connects data points gathered via remote sensing into a seamless digital surface. The concept of cell area and the depth, cell area and the cell depth. Cell, each cell in the grid has a fixed horizontal area and a specific vertical depth or elevation value. By treating each cell as a 3D block, by treating each cell as a 3D block, civil engineers can conclude or calculate the volume of specific slices of a landscape or a water body. This process allows GIS software to instantly calculate the total space within a reservoir or the amount of earth moved at a construction site by adding up the volume of every individual cell in the grid. The cell area and the cell depth itself suggests that the actual accumulation of sedimentation by using the digital elevation model. This, the capacity loss percentage is also one of the factors where the total capacity of reservoir will be affected or will be represented, where a portion which will be explained with respect to the 100% to the n number of percent. Just like 20% lost capacity by the sediment and 80% is of the useful life or useful storage of water. Means the portion is occupied by sediment instead of water. In the GIS environment, this lost capacity is the difference between the original bathymetry or the bottom depth and the current digital elevation model created via remote sensing. Civil engineers use this to turn raw cubic meter volume data into a simple percentage that stakeholders and decision makers can easily understand. Once the percentage reaches a certain threshold, GIS-based analysis helps engineers to decide whether to perform the manual removal, is also called as a dredging, or the flushing sediment out, is also called as a sluicing, or in extreme cases, the entire structure will be demolished. Moving towards the GIS workflow, especially interrelating the multiple types of information to calculate volume change. So there are four stages: data acquisition, just like input; surface modeling, which is the processing part; spatial analysis, which is the analytic or overlay concept; and at the end, visualization, which is the representation of output. So data acquisition, which is the input process, begins with collecting the raw data from multiple sources. Civil engineers use that remote sensing or satellite imagery to monitor surface changes, and bathymetry, just like sonar from boats, to measure underwater depths, providing the input layers needed for the digital model. Surface modeling, which is the actual processing technique based on the interpolation, sensors only collect the individual points but engineers use mathematical processing technique like triangulated irregular network. These methods interpolate in the gaps between known data points to create a continuous, smooth digital surface of the terrain. At the third part, the overlay or the cutting filling spatial analysis phase, different data layers such as the original ground level and the current sedimentation level are stacked or overlaid. Using cutting and filling analysis or cut fill analysis, the GIS software calculates the difference between these layers to determine the exact volume of material added or removed. Material added means filling, material removed means cutting. At the end, visualization, which is the output representation, is a volume difference map, which is a volume difference map. This colored coded heat map allows engineers to see the spatial distribution of volume change at a glance, making it easy to identify critical hotspots that require immediate maintenance or drilling. GIS application in the design of dam. The key engineering decisions are based by using the GIS application, where the dead storage sizing, GIS driven site selection criteria, lifespan, and the failure analysis are the basic components. So, in dead storage, engineers use GIS based modeling to predict the projected sediment level over a 50-year or a 100-year period. This allows them to position intake gates high enough so they don't get delayed or closed or clogged by accumulating mud, sediments, etc., ensuring the dam continues to provide water even at the bottom fills up. GIS driven site selection, which is using by the GIS technique, remote sensing identify high erosion potential by analyzing the digital maps of steep slopes and weak soil types across the watershed. Civil engineers use this GIS scanning to avoid building dams in areas where heavy sediment inflow would rapidly fill the reservoir and shorten its life. The lifespan analysis by calculating when sediment will breach live storage. Sediment accumulated in the live storage where the live storage level will be minimized. The engineers can determine the functional year of failure. This analysis is vital for long-term infrastructure planning and deciding when a dam will be eventually need major maintenance and repair works. At the end, by the comparison, traditional versus geographical information system, the left side shows a hard-drawn topographic map where calculations are discrete and slow based on the contours. In contrast, the GIS site displays a 3D digital surface that is dynamic and automated, allowing engineers to process complex terrain data in seconds rather than days. Efficiency and accuracy point of view, the GIS integration replaces tedious manual integration with automated volume calculations. By using continuous raster modeling instead of simplified contour lines, engineers achieve much higher precision when estimating reservoir capacities or earthwork volumes. One of the most significant advantages of GIS is the ability to overlay different information layers. By staking soil types, land cover, and elevation data, civil engineers can pinpoint exactly where erosion is starting in the watershed, moving beyond just measuring the sediment to identifying its source. GIS and remote sensing have revolutionized how we monitor and manage reservoir health. Instead of waiting years for a physical survey, we can now perform annual checkups using satellite data. This allows for proactive management, ensuring that our dams continue to provide water and power for generations to come. As you transition into professional engineering, remember that managing a dam is not just about the concrete structure. It is about managing the entire spatial ecosystem that fits it. Stay tuned, guys. Happy learning.